morning, everyone. Let's wait for some more seconds to wait for the people to connect. We will start shortly. I see the number of attendees is increasing. Let's wait for some more people to join in from the closing, or better, from the end of the opening session. I hope you enjoyed the opening session. Okay, we start in about 1 minute. Good, I think we can start. Good morning, good afternoon, everyone. My name is Maurizio Cocchi, and on behalf of the EUBCE, I would like to welcome you to this event, Market Outlook and EU-funded Research Innovation Actions on Sustainable Aviation Fuels. So the title in itself is quite self-explanatory. In this workshop, our aim is to listen to leading experts from companies and organizations that are both involved in market and industry initiatives in this growing market of sustainable aviation fuels, and also involved in demonstration and research projects funded by the European Union, mainly through the Horizon 2020, Horizon Europe projects, about what is happening in these projects. We have 5 speakers. We will first listen to an overview of the market outlook on sustainable aviation fuel by Tom Berg from SkyNRG, a company that everyone knowing about SAF has met many times in their life. Tommaso Barsali from Biofuels project from Record Italy, Green FlexJet project represented by Artur Majewski, and the Flight project, a very interesting demonstration project by Sabrina Geist from Fraunhofer, Germany, and finally Vincenzo Spallina from the Glamour project. I remind you that you can use the chat window in the platform to ask your questions. We will have a couple of question and answer sessions throughout the agenda. And of course, the entire event will be recorded and available very soon on the platform. So without further ado, I would like to introduce our first speaker, Tom Berg, from SkyNRG, with a presentation on the market outlook on sustainable aviation fuel. Tom, the floor is yours.
Yeah, thanks so much, Maurizio. I hope I'm audible and visible, and then the screen is visible as well.
Yes.
Thanks for the honor to kick off this workshop. I'd like to share with you a couple insights on how we view the market developing, which is of course developing very rapidly. There's a lot of momentum around SAF, also around SAF policy. And then maybe as a bit of an introduction to how we started this work. Actually, about a year ago, we started to revise our own company's 2030 strategy, and to be able to inform that position and to inform that strategy, we decided to analyze the European market, which at the time still had rumors on developing a sustainable aviation fuels mandate. And we were very curious to learn about whether there would be an oversupply or an undersupply of sustainable aviation fuels by 2030, 40, 50. And so we conducted an internal study, and actually that ended up being a market outlook. And then when we saw the conclusions, when we saw the results, we thought, okay, this is so relevant also for policymakers and the industry that we decided to make this public. And so now on a two times a year basis, we try to update this market outlook. And actually today, I'd like to share with you a couple insights around the outlook for the European Union, which is our second update. And then so, yeah, without further ado, I'd like to dive right in. I'm always a fan of starting a bit broad. And so I'd like to talk a little bit of the relevance of SAF first. So why do we see SAF as such a key lever? I'm a big fan of this graph because what it shows is the distribution of emissions across the type of flights that are being conducted, right? Commuter flights, regional, short haul, medium haul, and long haul. And what we see is that it's actually almost 3/4 of aviation CO2 emissions are in the medium haul and long haul flights. And as you can see also, if you go towards the right, those flights are very hard to decarbonize when using electricity or hydrogen. And potentially researchers think that hydrogen could be used in some form of a hybrid in those medium and long haul flights, but that technological limitations will actually restrict those type of flights to be run purely on renewable power, for example, or on hydrogen. And so that is why also, yeah, SkyNRG focuses so much on SAF. Our mission is to make sure aviation achieves its net zero goal by 2050. And because SAF is such a crucial lever for the short term, but also for the long term, we think that can make really the biggest impact in getting aviation to net zero. So that is why we focus on that, and why we also see so much momentum around SAF recently, and also a lot of policy mechanisms emerging. A little bit about SkyNRG. So I just said that we focus on SAF, but we didn't always used to also develop SAF capacity. Originally, when we were founded in 2009, we supplied the first airlines on sustainable aviation fuel, and we have been in this trading position for quite a long time, until a couple of years ago, we decided that there's a big wave of demand coming for SAF, and we pivoted into a SAF capacity developer. So as of today, we have about 6 capacity development projects around the world under development, based on a diverse portfolio of capacity projects around different technology feedstock combinations. As I said, we supply SAF to airlines, have supplied over 300 flights on SAF already. And we also help corporates achieve their emissions targets by letting them finance the green premium over SAF. So the difference between conventional jet fuel and sustainable aviation fuel, and they can use then these emission benefits for their climate targets. And as of this year, actually, individual travelers can also do the same through our platform, Fly on SAF. And last but certainly not least, we do not compromise on sustainability. And what we mean by that is that we take sustainability in very high regard in every decision we make. We have an independent sustainability board that is involved in every design choice we make, because those technology feedstock combinations that we establish, they'll be around for 20, 30 years to come, and we do not want to regret those decisions. So that is why we involve academia, we involve industry experts and NGOs into those kind of decisions. A bit on the projects that we currently have under development. So the ones that are in furthest development at the moment, I'll just focus on those. One plant in the Netherlands, 100 kilotons output based on waste oil inputs, is in feed phase at the moment, and we're currently also developing a facility in the Pacific Northwest in the US based on alcohol-to-jet technology, which is also in the project development phase. And at the same time, we're also working on a couple power-to-liquids projects, one in Amsterdam, Port of Amsterdam, and one in the southern part of Germany. So with that, I'd like to sort of dive into a bit of the momentum we see around policy. We've seen, of course, a sustainable aviation fuel mandate proposal last year in the July Fit for 55 package. But after that came also the Sustainable Aviation Fuel Grand Challenge by the United States, setting down an ambition for 3 billion gallons of SAF blending, or production, I should say, by 2030. So this is also really ambitious in terms of size. But I have to say, sort of the European Union framework is today the only long-term investment framework that really sets down targets until 2050, and also has the policy below it to back that up and actually incentivize sustainable aviation fuels. And then still then there are a couple of important differences, such as greenhouse gas thresholds, also where the burden is at, because the United States currently works with tax incentives. And that means that the burden of actually getting those sustainable aviation fuels financed lies with the average taxpayer. Whereas in the European Union, we have a mandate where it's mandatory to blend sustainable aviation fuels by 2030, and also going forward with other time intervals. And that means that actually the polluter pays, and so those costs will be borne by the actual tickets and the passengers that fly those planes. And furthermore, there are a couple other different sustainability characteristics around eligible feedstocks, but also the type of fuels that are incentivized. So power to liquids, for example, is not incentivized at the moment in the United States, whereas in Europe we have a solid sub-mandate for synthetic aviation fuels. Well, just to highlight that there are a couple differences, and that there's generally two flavors of SAF stimulation, and any stimulation of technology, by the way, and that is carrots versus sticks. And we see that in the United States at the moment, more carrots are being handed out, and in the European Union, it's mostly still the stick approach, where we see, okay, there's a need for a more balanced approach there as well, and to get those SAF capacities to scale. Then towards the conclusions of the outlook that we developed, to really analyze this market, and also to get a bit of a feeling for whether there will be an oversupply or an undersupply. We actually analyzed all of the renewable fuel announcements made in the European Union. And we looked at the underlying technology, had discussions with technology developers to see what the realistic SAF output could be of those plants. Also had a look at competing markets, such as the road and marine sectors, and how much of those renewable fuel outputs they would need to achieve their targets. And we arrived at an outlook where in 2030, we see about 2.6 million tons of SAF being produced by EU-based facilities. That is still about 1.4 million tons short of meeting the target. And what's interesting to see is that the predominant share of those outputs are produced by plants that use the HVO-HEFA technology, using waste oils as key inputs for those SAFs. And what's crucial to understand is that if you look at the available feedstock over time, we see that there's a certain ceiling that at some point is reached, because the supply of waste oils is inherently limited, right? If you look purely at UCO and animal fats type waste oils, you could develop new supply chains based on cover cropping systems or oil trees. But looking at purely the waste oils, there is a certain ceiling, and we see that with those announcements, that ceiling is more or less reached, and that actually the gap between the announcements and what needs to be achieved by the mandates should actually be filled by those non-HEFA pathways, such as gasification with Fischer-Tropsch, alcohol-to-jet technologies, but also power to liquids. And what's also good to understand is that the EU mandate also allows for imports of SAF. And so if in the event that, for example, also a cap on those waste oils will be in place, that's currently also under discussion in the EU mandate discussions, that means that this gap could still be supplied by imports from, let's say, Asia Pacific. So that's also a serious contender we see for those targets. Final point I want to make is that although this seems really ambitious, scaling the sector to these levels, it's good to understand that the 2030 targets only represent about 4% greenhouse gas savings compared to baseline, because we see a 5% blending mandate. Well, assuming an average of 80% greenhouse gas savings, that means 4% greenhouse gas savings overall. And that is, of course, by far not sufficient to reach a net zero aviation sector, or at least to get on track. And so we think there's more opportunity also for corporates and governments to really step up ambition there. Then briefly, the 2050 outlook. So because there's no planned announcements, of course, beyond, let's say, 2027, 2028, we wanted to get a feeling for how SAF supply could develop over time. And so we developed our own capacity growth model, using tried and tested metrics from academia and different think tank analyses. And so we arrived at this outlook where we see that there's a clear constraint for the HEFA pathway again, assuming that really novel pathways are in this base case scenario not developed, and that actually the real SAF growth should come from those cellulosic wastes and power-to-liquid type technologies. And also to get a bit of a feeling right for how much this is actually, because 40 million tons, that doesn't say a lot to many people. This can be translated to roughly 400 SAF plants of about 100 kiloton size, which we think currently is the bottleneck for many of those technologies. This can scale over time as bottlenecks are removed, but still this represents billion-dollar investments and a massive upscaling need for the sector. Finally, because I want to highlight that this base case is of course by no means a static picture. There are various assumptions underlying this, and various drivers can completely change this picture. I want to highlight a few of those drivers. First of all, competing demand, because if, for example, in the road sector we see rapid electrification, or in the marine sector we see different energy carriers taking off, lots of biomass could be freed up, which could be then allocated to SAF. So that's a possible scenario as well. We see sector growth being a key driver. So if the aviation sector recovers in a very limited fashion, it means that more biomass again will be available, and that more SAF could be produced versus the conventional jet fuel demand in the sector. Vice versa, because the assumptions we made in this slide are rather optimistic. We assume here that there's a constant jet fuel demand until 2050, but we all know that aviation demand will increase over time if no measures are introduced. And so if that happens, that means, of course, that the sector will need to produce more SAF to achieve those blending targets. Final point I want to mention before closing off is that technology development is obviously also a key driver to enable larger SAF volumes, because if those technologies are commercialized that turn cellulosic waste and really those low-grade primary residues into SAF, if we fail to commercialize those, then the technology challenge will even be, the feedstock challenge will even be harder. And so I think it's key that those technologies are developed and optimized to make sure that we can tap into the huge pool of feedstock resources that are out there. If you want to read more, because this was of course a very quick introduction on this market outlook, we have a whole document ready for you to read, a summary report, and as well as a background analysis containing all the assumptions. If you want to read that, just go to our website and download our May 2020 update. So with that, I'd like to close off, and I'm curious to hear if anyone wants to follow up or has any questions. Thanks.
Thank you, Tom. Thank you. Very interesting. And it seems like it's quite clear there is no room for other feedstock, other routes other than HEFA and HVO for the next, at least for the next 8 years. But then after we will see some interesting developments, hopefully, as per your projections. And this is a nice introduction to the next speaker. Although we will take questions after this second speech, and I remind attendees to put your questions in the chat inside the platform. And our next speaker is Tommaso Barsali from Record. He will talk about Bio4A project and hopefully also about the developments and the research activities that are being carried out by Bio4A, and not only, also the other projects. Many of them are developing solutions for alternative feedstocks other than oil-based feedstock. Okay, Tommaso, the floor is yours.
Good morning, everyone. My name is Tommaso Barsali. I'm a project manager and an agronomist.
Can you put it in full mode? Sorry.
Yeah. I'm a project manager and agronomist for Record Consortium, which is a public-private Italian consortium for research and demonstration in the renewable fields. I'll be presenting today some results and activities that we have performed for the Bio4A project, which is a project on advanced sustainable biofuels for aviation. And as Maurizio was saying, we'll be talking also about what Tom was reminding before on the constraints on the biomass to produce HEFA. So briefly, the project partners are Record, ENI, who entered in 2021, SkyNRG and then ETA Florence, Camelina Company, which is a company some of you may know already, specializing in the Camelina production, CENER from Spain, which is in charge of LCA, and JRC, which is in charge of very interesting activities on modeling what we could possibly and how we could possibly produce sufficient biomass in Europe for aviation needs. So briefly, the project concept is basically to demonstrate full commercial scale of HEFA production using residual lipids. And this is the industrial part, which is in charge of ENI. Actually, the objective of the project is to produce 5,000 tons of HEFA. That will be distributed in demonstration in commercial flights. In parallel, there is also very interesting, say, work, which is more investigative work on the supply of sustainable virgin lipids, while also recovering Mediterranean marginal land through the use of biochar, which is what we'll talk about more today. So as I was saying, ENI entered the consortium in 2021. There has been an extension, mainly due to some difficulties also linked to COVID. So the project will end next year. So I was saying, the problem here is to, of course, you produce HEFA to produce sustainable aviation fuel from residual lipids, but what can we do with virgin lipids? How can we sustainably produce virgin lipids while at the same time maybe also accomplishing some advantages, some advantages for other aspects, like mainly, for example, soil carbon sequestration. So together with Camelina Company and Record and also the other partners, we set up 2 experimental fields in Spain to test some of the solutions that I will explain now. We produced at Record, we produce biochar, which is you all very certainly already know, which is a negative emission technology through pyrolysis. We had the idea also to make a test with co-composted biochar. So it's not simply mixed compost and biochar. Biochar is introduced at the beginning of the composting process. The idea is to maximize the role of biochar and composts in a synergy as a soil amendment and as a soil carbon sequestration strategy. So this co-composted biochar and compost were distributed in agricultural fields in the 2 test locations. The results were quite good. So we had, aside from the carbon sequestration, which is of course a very important topic, but there is also an effect on productivity. This effect is incremental. This incremental effect is even higher when water availability is lower. So when water availability is very scarce from rainfall, which is a typical situation of the Mediterranean area, the biochar effect on productivity tends to be marginally higher. And this is because of this can be reasonably attributed to the capacity of biochar to retain water in soil. So biochar is a tool not only to stock carbon in soil, passively, but also to improve some characteristics of the soil, especially in marginal soil where rainfall is low. We also saw, of course, a positive effect of compost, where water availability was higher. So this is also an interesting feature of this strategy. Oh, I forgot to mention that in these two locations we were cultivating camelina. Okay, camelina is a brassica, which some of you may already know, oleaginous. So it's cultivated to produce oil, which is a very good candidate to be cultivated in regions where there is a tendency to drought, so to scarcity of rainfall. This was actually the activity, also an additional activity of Camelina company, which was to select a variety which could, let's say, which could fit very well the biochar agronomic protocol that we devised, which is under, and this variety has been selected through a selection protocol, typical, let's say, selection protocol, and is now under patenting process. At the same time, so these were basically very quickly the field trial results. What we devised also was an additional experiment with lysimeters. And for those of you who are not familiar with this term, it's basically a pot with a hole at the bottom, so that you can measure what is exiting the system. So you measure how much water exits the system, and in our case, we also measured the composition of this leachate, especially in terms of nitrogen, and the effect of biochar on this. So you can see from the graph at the bottom of the slide, a soil without biochar exits way more water than soil with biochar. So this might be one of the, let's say, more sensible explanations of why, with low water content, productivity of camelina was higher, because very simply there was more water availability. But this is a, let's say, quantitative proof of this feature of biochar in soil. There is also something on nitrogen. Maybe some of you already know there is a strong problem everywhere in the world, but also in Europe, concerning nitrate pollution in waterways, because agriculture uses, let's say, inorganic forms of nitrogen, which tend then to, in soil, to undergo a complex system of modifications due to microbiology, but also chemical and physical interactions, which result in nitrates exiting the system and concentrating and causing a considerable amount of pollution. So what we saw here is that through the introduction of biochar, there is a reduction in nitrates exiting the system, and also in the total amount of nitrogen exiting the system. So this is, let's say, a third feature of biochar in soil, used as an amendment, which is carbon sequestration, water, let's say, higher water availability for plants, and also an effect on pollution and reduction. So as I was saying before, we're doing all the partners of the project have been doing quite a lot of work on this project. We've also started a new agronomic field trial in Italy, a larger scale field trial than what we've been doing in Spain for the first 3 years. SkyNRG also has done a lot of work on this project, completing the business case and the market dynamics, for which we saw some very interesting features in the presentation made by Tom before. And we have a flight plan in place for the industrial part. There is a Joint Research Committee, JRC, made a very interesting work on the assessment of potential for what you could cultivate for virgin lipids in marginal land of Southern Europe. But well, yeah, it's more focused on Southern Europe and the Mediterranean area, building a sustainability index. So I will very briefly, I will present you some results. So before I'll make a short explanation on the cultivation of camelina in Spain. So basically, in arid region of Spain, or semi-arid region of Spain, the only cereal that you can reasonably cultivate, relying only on rainfall, is barley, because it's the less demanding cereal in terms of water and rainfall. But you cannot do barley every year. So in 1 year out of 2 or 1 year out of 3, you leave the land to fallow, which means you don't cultivate anything. The idea of Camelina Company was to introduce the cultivation of camelina in this fallow year. So this is quite evidently a sustainable practice by its own, because you don't displace any food production, and not only that, you also let's say you also increase the rotation, and you also have a positive effect on the yield of barley for the next years. You diversify also the opportunities for income for farmers. So it's a very good strategy, in my opinion. And this, what you see here is the model average change in yield in the camelina barley rotation in marginal land in 20 years, made by JRC. So as you can see, there is a good evidence of potential change also in marginal land. Of course, some of them are more even difficult to manage, but this model, it's the prediction of this model is that this strategy is actually a good strategy for yield. But there is not only yield, there's only soil organic carbon. So back to what we were saying, so we have to produce SAF, but we have to produce it sustainably. And one, let's say, very important sustainability feature is soil organic carbon, because it's also a win-win situation in which you not only decarbonize the aviation fuel, but you also actually physically stock carbon in soil. And as you can see at the bottom left diagram, very briefly, is that you have not only a yield increase by using the camelina and barley rotation, but you also have a soil organic carbon stock increase while using biochar at relatively low rates, like 4.8 tons per hectare. That you distribute once in 20 years. So this means that biochar is a very good alternative and complementary tool to decarbonize not only aviation fuels, but also food production. And it's perfectly, let's say, compatible and complementary to many other solutions that you can find in agronomy to, for example, reduce pollution or use more nature-based solution, while at the same time increasing productivity. So this is the last slide. Very briefly, we also performed as record activities on UCO pretreatment, alternative pretreatment pathways, which let's say should include a reduction in hydrogen consumption for pretreatment of UCO. So this is only I cannot present any result for the moment, but this is also a very interesting pathway to contribute to let's say decarbonize the aviation sustainable aviation fuel production. Okay, this is the end of it, and I'm very happy to hear questions, if any.
Thank you, Tommaso. Thanks a lot, and also for keeping the time. I don't know if you have questions from the floor, my colleagues. I don't think so for the moment. I renew my invitation to all the attendees to put your questions in the chat window in the platform. Well, for me, it is striking to see how it is more and more clear that finding solutions for one of our challenges, that is decarbonizing transports, aviation fuels, aviation in this case, can also enable a wide range of solutions for other challenges, and it is fully in line with the EU Green Deal. So by finding solutions for making flights more sustainable, we can enable solutions to make even agriculture more sustainable and more resilient to climate change. And this is really, really interesting from my point of view. Okay, with this, I would like to introduce my colleague Stefano, and he will take over the other presentations. Stefano, the floor is yours.
Thanks, Maurizio. Can you hear me? Perfect.
Yes.
Thank you very much. So thank you to the previous speakers. Now I'm going to introduce the next one, and Artur Majewski from University of Birmingham, United Kingdom, will present the Green Flex Jet project, sustainable jet fuel from flexible waste biomass, another European funded project on, of course, SAF production. So, Artur, the floor is yours.
Thank you, Stefano, for introduction. Let's see. I want to share the presentation. Can you see it now?
Yes, but please put it, switch the video. You can see it only in preview.
It's now okay?
No, it's the same.
The problem. You should be able now to see the
main screen, Artur.
Okay, I will try to share my, sorry for the confusion.
Sorry, Artur, are you using an Apple, so iMac, a Mac computer?
No. But I'm connected through Zoom, so maybe that's the problem.
Are you using double screen or one?
Now we should be able to see.
No,
Fine.
Thank you.
Okay, sorry for. So thank you, Stefano, for introduction. I'm a project manager for Project Green Flex Jet, and in this short presentation, I will describe quickly the project Green Flex Jet. So the project started in 2018 and will finish in 2024. We had some technical difficulties in the project, but after the amendment a few months ago, we restarted the construction of our demonstration plant. The total budget of the project is around 19 million euro, with 10 million euro from European Commission, and the project is part of the Horizon 2020 research program. We have a consortium of 12 partners from 5 European countries, and the main goal of this project is to construct a pre-commercial demonstration plant for the production of around 1,200 tons of sustainable aviation fuel from waste vegetable oil and waste biomass. And at the same time, we are mapping the economic and social and environmental impact of the technology. The project is coordinated by the University of Birmingham, who have all range of partners responsible for providing the main technology to the project, for developing feedstock, site operation, product testing, supply chain. We have partners that analyzing environmental and social analysis, and partners responsible for dissemination of this project. To this audience, I don't have to say much about importance of SAF. I would like just to highlight that the aviation is responsible for over 3% of greenhouse gas emissions, and it will continue even more, be even more significant as other sectors will be decarbonized. You've seen this slide on a previous presentation from Tom. What I would like to highlight here is that the HEFA technology is growing very quickly from almost zero at 2020. We will reach a few millions of tons SAF in 2025. But what is also important is that this technology very quickly will reach its capacity because of the limited feedstock supply. This is why in our project we are not looking only on the HEFA, but also on conversion of bio-oils to jet fuel. Our project is demonstrating two main technology. One is the conversion of waste vegetable oil into aviation fuel, and second one is to provide hydrogen for this technology from organic waste. So we have the waste cooking oil that in transesterification process is converted into crude biodiesel and glycerol as a byproduct. The crude biodiesel after purification step is delivered to the hydrotreatment plant when we have hydrodeoxygenation and hydrocracking of this product. The organic fraction is delivered to the fractionation column when aviation fuel is separated from biodiesel and bionaphtha. The plant will be optimized to intensify the yield of aviation fuel. This process required a lot of hydrogen, so this hydrogen we supply from pyrolysis of organic waste. In our case, we use digestate and waste wood. We use thermocatalytic reforming that combines pyrolysis with reforming reactor, and we produce syngas, bio-oil, and biochar. Hydrogen is separated from syngas using pressure swing adsorption. The bio-oil we also convert using hydrocracking, hydrodeoxygenation, and fractionation into aviation fuel. However, on much smaller scale, this is because this route is not certified yet for the commercial fuel production. However, we hope that our results will add something for the certification process. The produced biochar in gasifier is used to generate heat and power for our plant. The site is located in Barclay in UK, not far from Bristol. On the screen you can see the plot plan of our plant and 3D representation of those units. We have the tanks of bio-oil, transesterification, hydrotreatment plant, and this is the TCR plant. Close to Barclay, we have airports in Bristol and in Cardiff. However, those airports have limited options for blending. This is why we target more airports close to London. The transesterification module is already ready, is on the site. Other components are under construction. You can see some of them on the current stage on this slide. We hope that according to the schedule, we should complete construction of this plant at the end of this year, with commissioning at the beginning of the next year. So at this time, the next year, we should be able to report to you production of first batches of fuel from waste cooking oil and waste biomass. Next year also we hope to organize several open days at our plant during the fuel production, so if you will be interested, you could visit us next year. If you need more information about our project, please visit our webpage. And that will be all, I think.
Perfect. Thank you, Arthur. Thank you for your presentation and for information news from Green Flag Jet project. So we will see if some questions will arrive in some minutes. And now, Sabrina Geist from Fraunhofer, Germany, will present flight project, fuel via low carbon integrated technology from ethanol.
Right.
Another European project. So, hi, Sabrina.
Hi.
The floor is yours for your presentation.
Thank you. I would just check.
Fine, we can see it.
Yes. Okay. So yes, hi everyone. So yeah, a warm welcome from me as well. So my name is Sabrina Geist. I'm a research associate and project manager at the Fraunhofer Institute for Material Flow and Logistics in the...
Sabrina, one quick point, your Word files in the presentation, don't worry about it, but if you move it to your other screen, that's great.
Oh, sorry. Sorry.
No problem.
Yeah,
great.
I've got some, I don't know, technical issues, I think.
No, you're good. Good to go. We can see your screen now, so it's all fine. This is great.
Okay. My name is Sabrina Geist. I work for the Fraunhofer Institute for Material Flow and Logistics in the Department of Aviation Logistics based near the airport in Frankfurt in the EU research project FLIGHT, so the short form for fuel via low carbon integrated technology from ethanol, which I would like to briefly introduce to you today. We are mainly responsible for communication and dissemination, but also for the clustering with other EU projects. So FLIGHT is supported by a consortium consisting of 5 partners, as you can see on the in our partner map on the right-hand side. So besides us, we have SkyNRG as our project coordinator, who's responsible for the overall project management. The downstream supply chain and the SAF contracting. We have LanzaTech, which has taken on the role as our technology leader and operator. We have E4Tech, which will conduct the life cycle assessment, and RSB will prepare the RSB certification. In general, our aim is to build Europe's first of its kind alcohol to jet production plant, which is expected to produce at least 30,000 metric tons per year of SAF. Main feedstock will be ethanol derived from waste-based resources like agricultural and forestry residues, starch slurry, and industrial waste gases. With the help of our project, we would like to demonstrate the flexibility of ethanol-based ATJ technology for meeting the needs of commercial aviation and to monitor the technology from a technical, environmental, economic, and also socio-economic perspective. Yeah, the ATJ technology. So in the LanzaJet ATJ process, ethanol from any source is chemically converted to synthetic paraffinic kerosene, so SPK, via the 4 steps. So dehydration, oligomerization, hydrogenation, and fractionation. The ethanol is first dehydrated to ethylene. The ethylene is then oligomerized into longer carbon chains. The carbon chains are then hydrogenated. And yeah, finally, the product is fractionated to isolate the ATJ SPK jet fuel as a stable white boiling paraffinic kerosene that has superior properties compared to conventional jet fuel, including improved energy density, freeze point, and thermal stability. The remaining fraction is synthetic paraffinic diesel, so a renewable diesel fuel with also superior properties to conventional diesel. The product slate is as much as 90% jet and 10% diesel. In general, you can say that flight is the first project that covers everything. So really from the beginning till the end. So really from the feedstock to the supply of SAF at the airport. So once the SAF is produced at the flight facility, it will be blended with conventional jet fuel and transported to the airport. This blending is required to meet the current commercial aviation specifications. And according to those specifications, flights SAF can be blended up to a maximum blend of 50%. After blending, it becomes a so-called drop-in fuel, meaning that it can be used by existing aircraft without any engine modifications. So really a major advantage of SAF compared to other carbon reduction alternatives. This also applies to the way what the SAF blend is delivered. So it can be used to refuel an aircraft via the existing fueling systems at airports. So like, the normal ones which currently fuel aircraft with fossil-based jet fuel. The SAF produced at the flight facility will be delivered in this way too. Discussions on offtake agreements for who will purchase the SAF from the flight facility. So really in order to reduce their emissions from flying ongoing. So when these agreements are in place, the most logical transport option, of course, based on the delivery location, will be selected. And yeah, the delivery can be made via pipeline or train, barge, or really truck. And our goal and intention is to achieve RSB certification for our facility in the end. Yeah, and last but not least, maybe a short update on our current activities. So the basic engineering package for flight is complete. So really the feed front end engineering phase is complete. This means that the process and main equipment design is defined together with the material selection, the overall layout of the plant, the electrical and instrumentation design. And all key HSE studies have also been performed to ensure the plant design is safe for people and, of course, the environment. Yeah, and if you would like to get in touch with us, or if you want to find out more, you can, of course, visit our social media channels or our website, or yeah, via mail. And yeah, thanks a lot for your attention. And if you have any questions, my partner from SkyNRG, Oscar, and I, we are very happy to answer your questions. Thanks a lot.
Okay, thanks, Sabrina. Thanks for your presentation and for the introduction of presentation of flight project. So, Maurizio, do you have?
Thank you, Stefano and Sabrina. I think we are right on time, and I don't see the last speaker yet, Vincenzo Spallina. As I said, might join a bit later. So while we wait for a few more moments to see if he eventually connects, I would like to address one question to the SkyNRG team. Maybe I got it right. I got it wrong from the presentation, the initial presentation on the market outlook, but I think I got it that even in the post-2030 scenario, so once the alcohol to jet and Fischer-Tropsch fuel value chains are expected to update to increase, I think Tom mentioned that in their scenario they still foresee a large need to cover the European demand for feedstock through imports of feedstock, I guess. So and this, so I was wondering if that's correct, or maybe I got it the wrong way, because I would expect that once we have removed the barrier of using only the oil-based feedstock and the other value chains take up, we could enlarge the feedstock base and also use the many untapped resources that we have on other types of lignocellulosic feedstocks. What's your opinion on that? Or maybe it was just my wrong interpretation?
Yeah, I can comment on that. So what's I think good to understand is that the key assumption in the analysis is that towards 2050, we assume that at least for the HEFA pathway, there's no other feedstocks developed aside from the waste oils, and so any other types of feedstock would have to be imported or still have to be developed. But what I meant in terms of feedstock is that, what I meant when I said imports is that it needs to be imports of actual SAFs. And so the European mandate allows for that SAFs are imported and not the feedstock itself. I think a lot of feedstocks, especially the primary residues that contain a lot of moisture, they're difficult to ship around the world. It will be very, very expensive to do. Only the really energy dense type feedstocks, those I think would be, you could find a business case for actually importing those. But I think you're right. Also as we develop more technologies, we could access more domestic feedstocks, and we would have to rely less on imports. So I think that's also an important takeaway.
Thank you. So with this, I'd like Stefano, do we have any other questions? I don't think so. So if not, I think I'll ask our colleague Clara if she can already start.
Maurizio, there is a question.
Okay.
Liam Mannion. For all speakers that mentioned LCA. What are the methods you use for LCA?
Good question. So this is probably for Sabrina, and I don't know if Tommaso can reply. I think SkyNRG from Biofuels would be more suitable for this reply, but I'm not sure. What kind of tools do they use? What tools do they use for the LCA analysis?
I can answer for the flight project if that's helpful. We are RSB is one of our partners, so we're using the RSB tool to calculate the LCA emissions, and they are also one of the certification schemes under, for example, the Renewable Energy Directive to certify and audit the eventual emissions in a realized supply chain. But for the modeling exercise, we're using their tool to calculate the LCA emissions.
Thank you, Tommaso, and then Artur, maybe.
Yeah, I know I'm not in the best position to reply to this question because I would need to have some advice from our partners from SkyNRG. But the main tool used for the LCA evaluation is FEMA-Pro. From this is the information I have.
Good.
From our case, I would say that Tom answered our question because SkyNRG is in our consortium, so they are also involved in this.
Good. Fine. Thank you.
May I ask a question to Sabrina? What
Yes,
kind of hydrogen are you using? Is it green hydrogen for the process? What is the source of hydrogen?
Yes, for the flight project, we haven't selected that yet, but it's going to be green hydrogen, yes.
Oh, thanks.
Fine. Do we have any other questions? I don't see any in the chat. Okay, if not, I would leave the time for the last presentation, and maybe we still have 5 or 6 minutes for discussion between the speakers. Our next speaker would be Vincenzo Spallina from the University of Manchester, presenting about the Glamour project, but unfortunately he couldn't make it in time, so he sent us a recorded video. And I'd like to ask my colleague Clara to launch the video. It's a rather short one. Clara, can you launch the video? Clara? Okay, just a second.
Good morning, everyone, and thank you for the opportunity. I'm Vincenzo Spallina from the University of Manchester, and I'm the project coordinator of the Horizon 2020 Glamour project, which stands for Glycerol to Aviation and Marine Products with Sustainable Recycling. In this presentation, I will go through the consortium, the project overview and objectives. I will show you some information about the actual status of the project, the impact, and what are the main conclusions so far. So consortium, Glamour includes 10 partners in over 6 different countries. We have 2 universities, which is the University of Manchester and the Eindhoven University of Technology, 3 research centers, TNO from Netherlands, TU Vito from Belgium, and CSIC from Spain, 2 small medium enterprises such as CNCS and Ineratech, and finally 3 large industry, which are Argent Energy, Sirtechnigi, and P&O Chowtech. The overall budget is about 5 million, and we also have an industrial advisory board, which includes Johnson Matthey, ENG, SkyNRG, and Total. Now, what is the idea of the technology? So imagine the existing first and second generation biodiesel plant. While producing biodiesel, there is always about 1 kilogram, so every 100 kilograms of biodiesel produced of glycerol. This glycerol is often very, especially for second generation plant, very polluted by different components. So what we do is that we aim to refine the glycerol, get a feedstock, use this feedstock for syngas generation with an appropriate hydrogen to CO ratio, and at the same time produce a stream of water and CO2, which could be further used for CO2 utilization or for negative emission with CCS. And the syngas generated will then go in a fuel synthesis part where basically our main products, which are aviation fuel or marine fuel, can be produced. Now, the main technology that we are going to demonstrate are the syngas generation, the fuel synthesis, although we are also doing quite some substantial research in the area of refining. In terms of project positioning, there will be a development in key component production and scale up. So there is quite some substantial research in material manufacturing and lab scale testing. We will move on to prototyping. That's the case where we will build up our TRL5 demonstration. And together with that, we are also covering industrial application, which obviously includes biodiesel production as well as transport biofuel for hard to decarbonize sectors such as aviation and shipping. What are our main objective and key performance indicators? So we aim to demonstrate that to TRL5, the integrated system, syngas generation and fuel synthesis, and operate for 1,000 hours with a feedstock of 2.5 kilogram-hour, overall resulting in a thermal input of 12 kilowatt, producing 120 normal liter per minute of syngas, and overall resulting in a sync-crude production of 0.5 kilogram-hour. We aim to scale up advanced material up to 15 kilograms for syngas generation and 1 kilogram for 3D printed cobalt-based Fischer-Tropsch synthesis catalyst. In terms of key performance indicator, we aim to achieve a carbon efficiency around 45%, primary energy efficiency around 65%. In terms of, we expect to have between 17 and 20% yield, capex reduction of 30%, opex reduction of 20%, up to 20%, and CO2 emission reduction above 70% compared existing gas to liquid processes. In terms of market and business, so in terms of expected outcomes, we expect to have also a potential market which can reach 9 million tons a year of new feedstock and make a business case which could cover micro to large scale plant for the production of biomass to liquid fuel. Now let's go through the different work package. Work package 2 is the one on industrial application. What we have done so far, we have basically done a feedstock market study, in particular looking at possible price and existing market in Europe and China, as well as also we have seen main performance and KPI for existing gas to liquid and biomass to liquid plant. We are also defined a certain methodology, so while including most general in order to make sure that this could be applied to different systems, and we are currently doing a flow sheet analysis simulation to make sure that we can calculate our different performance. In work package 3, we are working on syngas generation. That's work package leader in CSI-SIC. So here we are looking at the feedstock purification. These are main results we have seen already in our laboratories. We are also doing some multi-scale testing at different sites for syngas generation and along with material development for glycerol chemical looping reforming, and doing also some modeling to basically identify the main mass transport phenomenon occurring during this process. In terms of work package 4, we are looking more at fuel synthesis. So that's the case of Fischer-Tropsch project. The work package leader is TNO. Here we are producing new material formulation, mostly cobalt-based. We are also testing this unit into different plant in TNO and in Aerotech. And the other novelty is to basically 3D print a new catalyst, which will be then used for to enhance performance. And what we are doing at the same time is also some modeling, in particular the EAT models to see what is the thermal performance of conventional catalyst versus 3D printed catalyst. The demonstration is work package 5, so we have already defined the main PNID, and we have already purchased some main component. You can see here the reactors that will be used for the syngas generation, and we also have bought already the one for the fuel synthesis. So we are at the process to build up the new plant. The final work package is about life cycle and sustainability assessment. So here, basically, we are looking from one end is the life cycle assessment. So we are starting from the results at laboratory scale. We are trying to scale up also the life cycle performance, in particular to identify already at the early stage what are the key elements that will reduce or improve life cycle performance. So that's, which basically means what are the key process within the manufacturing and the operation process that will require more attention and change, and possibly a different assessment from an environmental perspective. We are also looking at the same assessment from a social perspective, and at the same time there is also Ineratech, which is looking more on the policy analysis, in particular what are the key action needed to enable this technology and being developed at scale with an appropriate market in the future. Finally, in order to have the project looking at exploitation and dissemination, Glamour has a website. You're all invited to visit the website and register in our newsletter. We distribute a newsletter every 6 months with the main results of the project. We have already we are already networking with more than 10 projects, and that's the reason why we are actually here, or we did with other projects like we did to Fuel recently. Stakeholder analysis, we are studying any possible stakeholders which will take part and will be interested to develop this technology in the future. So we do not limit our study to our partners, but we aim to embrace a large number of companies. And basically that's the way we are trying to also inform the other projects and the other partner. In terms of exploitation, we have already defined the APR agreement, and we have already run a first exploitation workshop. This means that we have already identified which one are the main key exploitable results, so in terms of material, process, and also services. Few words about the impact. So as I said before, we aim to produce advanced biofuel from bio-waste with a decrease of the cost of existing Fischer-Tropsch-based fuel synthesis up to above 65% of the existing cost. We aim to scale up this technology to achieve up to 15% of aviation-based GHG in Europe. This will be not only with glycerol, but covering a vast amount of bio-based feedstock, including biogas, for instance. And we expect that this could be able to generate a business which is 11 billion per year in up to 2040. Which basically means that is a business which is very scalable, and one of the main reasons is that the technology can work at small scale as well as large scale, and because the technology can also be flexible not only in the feedstock side but also on the product side, as not only liquid fuel but also methanol or hydrogen could benefit from this technology. Saying that, I would like to thank you first of all, the European Commission for giving funding to this project. I would like to thank all the partners which are working on the project in the last 2 years, despite the situation and the pandemic, which has never allowed us to meet, and this will happen in a week's time. And on top of it, I would like to thank you, all of you, for your attention.
Good. Thank you, Clara. Unfortunately, Vincenzo is not with us to reply to questions and to the discussion. Stefano, we need to go to the final words also because we are quite strict with the timing and we need to close very soon.
So I think many information on SAF production our presenter gave us, and in particular about very, very interesting European projects, ongoing European projects. So I think we have very, very good opportunities for the future regarding the sustainable aviation fuel production in Europe and of course in other international countries. So I would like to thank you all of the speakers and Maurizio for his chair of this workshop. And if you want to conclude, Maurizio, this workshop.
Yes, I would also like to thank all the speakers and the attendees and remind you that you will find the recordings in the platform, and I invite you to continue to interact through the networking tools that we have, the public forum and the want to meet button and the schedule meeting button, everything that might be useful for you to interact with the attendees throughout the conference. And I wish you a good to enjoy the continuation of the conference. Thank you and have a good day. Bye-bye.
Thank you. Bye.
Bye.
Bye.